Polar coordinates. It's just a different way of representing points in the plane. So we're going to graph polar coordinates. We're going to determine multiple representations because unlike rectangular or Cartesian coordinates, the way you label them is not unique. Just like the unit circle, there's different ways to get to the different angles. And we're going to convert both points and equations back and forth between Cartesian and polar. So, Cartesian or rectangular coordinates, we have a horizontal and a vertical component. Polar coordinates go around in circles. They are r and theta. This is the radius, and this is the angle. So the first term is called the radial component. I called it the radius. The second is called the angular coordinate, and I just called it the angle. The origin is now called the pole. And we move around the pole just like we do the unit circle. So theta is the value amount of angle that you move from the positive x-axis. So plotting points. It's scaled just like the unit circle is. So here's a sheet of polar graphing paper, which helps me a lot when I'm graphing these things. And I do have some blank polar graphing paper that you can print out and use to practice and you do your homework. So to plot 2 pi over 4, we move to the right 2 units along the positive x-axis, and then we move to pi over 4, which would be right there. So this is the point 2, comma, pi over 4. It is also the point 1, 2, and negative all the way around this way. So 2 and negative, let's see, this would be pi over 2, 7 pi over 4. But you can also plot points with negative x values. So let's see if the next page has one of those. No. So I'm going to go ahead and show you how to plot one with a negative x value. We would have negative 3 and pi over 4. There's 2 ways you can think of it. Either you move 1, 2, 3 in the negative direction and then go down pi over 4, so negative 3 pi over 4. Or you think about moving 1, 2, 3 units in the positive direction, moving 1, 2, 3 units in the positive direction, so pi over 4 units in the positive direction, and then just reflect it back over the pole. So that's how we plot negative points. Let's just practice some points on a polar grid. So this will be example 1. We want the point 3 and pi over 2. So I move over 1, 2, 3, and then I move up to pi over 2. 3, pi over 2. 4, 7 pi over 6. So 4 units over, and then I go to 7 pi over 6, which is right over here. Now, yeah, if you wanted to say, oh, look, here's 7 pi over 6, and then just move 4 units, that's fine. So 4, 7 pi over 6. There's the pretty pictures. Here's where I talk about plotting a point with a negative component. So this time I chose -2 and pi over 6. So I'm going to turn back over to this side and plot the point -2 and pi over 6. So move pi over 6 in the counterclockwise direction. So move pi over 6 in the counterclockwise direction. So here's pi over 6. Extend a directed line segment 2 units into quadrant 1. So 1, 2. And then trace back over it and go 2 units into quadrant 3. So this is the point -2 pi over 6. Or move pi over 6 in the counterclockwise direction and then draw the directed line segment from the pole 2 units the negative direction into quadrant 3. Like I said, I generally would just go 1, 2 units in the negative direction and then go down to negative pi over 6. Any of those ways will get you to the right spot. So let's compare 2 and pi over 6 and -2 and pi over 6. So 2 pi over 6, you start at the positive and move pi over 6 units up. Here you start at the -2 and move pi over 6. You're still moving pi over 6 in the positive direction because counterclockwise is the positive direction. So let's practice plotting some points. Get some graph paper out and you try, and I'll try, and then we'll come back and compare our points. Let's compare 3 and -pi over 6. So I would move to the right 1, 2, 3 units, and then -pi over 6 means I move in the clockwise direction, pi over 6 units. A lot of other ways we could represent that. It could be 3 and 11 pi over 6. If we wanted everything to be positive. 2 and 9 pi over 4. So I moved 2, and then I went 4 pi over 4. I ended up down here. 8 pi over 4. And I end up at 9 pi over 4. I come back up here to pi over 4. So this is the same as 2 and pi over 4, because you remember from Unit 1, 9 pi over 4 and pi over 4 are coterminal angles. So for every coterminal angle, you have another way to represent a polar coordinate. And now the trickiest one, we have a negative number, so I move to the left for my starting point, and then I have 2 pi over 3, and that's negative as well. So instead of moving in the positive direction, I move in the negative direction, pi over 3, 2 pi over 3. And again, this is exactly the same thing as 5 and pi over 3. Lots of different ways to represent the same points. Well, not only are we going to plot the points, we are going to convert back and forth between rectangular or Cartesian and polar and back again. So let's look at, just remind ourselves that cosine of theta is x over r, if you're thinking about SOHCAHTOA. So x is equal to r cosine theta, and y is equal to r sine theta. So if we want to write polar coordinates as rectangular coordinates, we have our r, we have our theta. So this is example 2. We start with 3 and pi halves. That converts to 3 cosine of pi over 2, 3 sine of pi over 2. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so this is the point 0, 3. Next one we have -2 and 0. So that's -2 times the cosine of 0 and -2 times the sine of 0, which is -2 times 1, -2 times 0, which is just -2, 0. And then we have -1 and 2 pi over 3. That would be -1 times the cosine of 2 pi over 3, -1 times the sine of 2 pi over 3, which is -1. Cosine of 2 pi over 3, 3 in the denominator, cosine's a half. 2 pi over 3 is in quadrant number 2, so -1/2. And then -1 times sine of 2 pi over 3, square root of 3 over 2. So this is 1/2 and negative square root of 3 over 2. And now let's think about this, because these two were really kind of obvious. If I were to graph this, I would move to the left 1 unit, and then I would move 2 pi over 3 in the positive direction, which would bring me over here into quadrant number 4, where the x-coordinate is positive and the y-coordinate is negative. So yeah, it makes sense. Good error checking. There's the pretty answers. Now if we need to convert back, then we use the fact that r squared is equal to x squared plus y squared, and Pythagorean theorem, and tangent of theta is y over x. So let's convert 3, 3 to polar coordinates. So 3, 3. So we need an r. R is equal to the square root of 3 squared plus 3 squared, which is the square root of 9 plus 9, which is 3 times the square root of 2. And now we need our theta. Inverse tangent of 1, 3 over 3. So let me go ahead and write it as 3 over 3. So you don't look at this later and say, where the heck did that 1 come from? Is pi over 4. And just like when we're doing vectors, we have to make sure that we're in the right quadrant, and yes, we are, because the rectangular point 3, 3 lives in quadrant number 1, and then the point 3 square root of 2 comma pi over 4 also lives in quadrant 1. Boop. Pretty answer. Okay, there are lots of other rectangle or polar coordinates that represent the point 3, 3. You could have negative square root of negative 3 square root of 2 with 5 pi over 4. So let me get another piece of paper. So square root of 3 and pi over 4. So square root of 3 times 2. I'm going to have to get a decimal approximation for that. 3 times the square root of 2. Second square root of 2 equals. So it's about 4.24. So I'm going to put it at a little bit bigger than 4. So right here is 3 square root of 2 and pi over 4. Now if I move negative 3 square root of 2, so right over here, and then went 5 pi over 4 units in the positive direction, well, here's 4 pi over 4 units in the positive direction. 5 pi over 4 units brings me to exactly the same place. Negative 3 square root of 2. And 5 pi over 4. If I go positive square root of 3 square root of 2, and then I move in the negative direction 7 pi over 4 units, so 4 pi over 4, 3 pi over 4 more units, then yes, indeed, I end up back at the same place. 3 square root of 2. I don't know why I keep wanting to put an extra comma in there, and negative 7 pi over 4. One more way we could get there without having to resort to coterminal angles. We could move in the negative r direction and the negative theta direction. So we could have negative 3 square root of 2 and negative 3 pi over 4. So there's always 4 ways without even getting off the unit circle where you can be between 0 and 2 pi. Okay, so practice, try these out, and we'll meet back and compare answers. So first, I just found my radius by negative 4 squared plus 4 squared, which gives me the square root of 16 plus 16, which is the square root of 32, which is 4 times the square root of 2. As soon as you see you have 4 squared plus 4 squared, you know that it's just 4 times the square root of 2, because you got 2 4 squareds living in there. But then we took the inverse tangent of 4 over negative 4, which is minus 1. Inverse tangent of minus 1 is negative pi over 4. We need it to live in quadrant 2, so we choose 3 pi over 4. This time my radius was negative 3 squared plus negative 3 times the square root of 3 squared. So that's 9 plus 27, which just happened to be a nice, friendly, perfect square. We get 6. I did inverse tangent of the y-coordinate divided by the x-coordinate. Gave me inverse tangent of negative 3, negative square root of 3, which is pi over 3. But since I need to be in quadrant 3, I used 4 pi over 3. So now we're going to go from just converting points to converting equations. And we're going to use the fact that, this is example 4, x squared plus y squared is equal to r squared. And we'll use the fact that x is equal to r cosine theta and y is equal to r sine theta. So first one, we have the Cartesian coordinate equation, x squared plus y squared equals 9, which happens to be the equation for a circle centered at the origin with radius equal to 3. But we know that x squared plus y squared is r squared. So r squared is equal to 9. So r is equal to plus or minus the square root of 9, which is plus or minus 3. And if you graph those things, you get the exact same answer. I'm going to pull up Desmos and prove it. Now, when I'm graphing these things in Desmos, I like to go up here to the little graph settings and put it into polar mode. Yeah, Desmos will do that for you. Although it still graphs the coordinates as rectangular. So if you put in 1, 1, it'll be the Cartesian point 1, 1, not the polar coordinate 1, 1. So let's do x squared plus y squared equals 9. So exactly like I said, it's a circle with radius 3. If I put in r equals 3, it's the exact same circle. If I put in r equals -3, it's the exact same circle. So these are 3 different ways to represent the exact same circle. There's my pretty answer. Right, let's see. X squared plus y. I have the same example there twice. And yeah. And then I gave a different solution. Okay, so I will fix that. Example 5 is supposed to be x squared plus y squared equals 6y. So we'll take care of that. But I'll write it down correctly. Example 5, x squared plus y squared equals 6y. And now I'm going to hide the answer so you don't see it. So I use these equations here, these relationships, x squared plus y squared. So r squared is equal to y is equal to r sine theta, so 6r sine theta. Well, r isn't going to be 0 because then it would just be the pole, and we wouldn't have x squared plus y squared equals 0. So I can divide by r, and r is equal to 6 sine theta. And now we can look at the pretty answer with the pretty graphs. So this one I had already graphed for you. R equals 0 is a single point. So, okay, let's do another one. Example 6. Y equals 3x plus 2. Well, y is r sine theta. X is 3r cosine theta plus 2. Get all your r stuffs on one side of the equal mark. So r sine theta minus 3r cosine theta is equal to 2. Factor out the r. Divide both sides by the stuff sitting next to the r. Because your goal is always r equals something. R equals 2 over sine theta minus 3 cosine theta. And that's the equation of a line in polar form. There's the pretty solution and the pretty graph. So now practice. We have 4 of them here for you to practice, see how you do. First couple, not too bad. Then they get a little more challenging, so we'll meet back and go over them. Okay, I felt pretty good about A and B. A was just another circle. Once you added x squared to each side, you ended up with r squared equals 3. So r was plus or minus the square root of 3. This one, I had r sine theta is 4r squared cosine squared. I divided both sides by r, so I ended up with sine is 4r cosine squared of theta. I divided both sides by cosine squared, and then I just switched them places because I like my r on the left-hand side. So I ended up with sine over cosine squared is equal to 4r, and I divided that into 1 over cosine times sine over cosine, so I ended up with secant of theta times tangent of theta, so r is 1/4 secant theta tangent theta. Then the next one, I was dubious if I had it right. I have 9xy equals 1. So that's 9 times r cosine r sine equals 1. So 9r squared equals cosine times sine. I divided both sides by cosine times sine. So 9r squared is secant times cosecant. So r squared is 1/9 of secant times cosecant. So r is plus or minus square root of this whole side. Square root of 1/9 is 1/3. And I did plug it into Desmos. And look at that. It's the exact same thing. Here's, there's the pretty Cartesian graph. There's the pretty polar graph. So now give part D a try. See how that goes. We'll meet back and compare. This one was pretty challenging. So first thing I did was I replaced x and y with r cosine theta and r sine theta. Then I had to FOIL. Then I combined my r squared cosine squared, r squared sine squared, and made them just r squared because cosine squared plus sine squared is 1. And then I thought about trying to factor that, but that sine of theta got in my way. So I had to resort to the quadratic formula. So negative b, plus or minus square root, b squared minus 4ac, b squared minus 4ac, all over 2a, all over 2a. Yeah, you do have to remember it. So there it is. I did some simplifying, and I almost lost my squared, and I got frustrated because I didn't know why it wasn't working. But then I realized I had lost my squared, and yeah, it's the exact same thing. So let's see what's next. Ooh, now we're going to go from polar to Cartesian or rectangular. Example 7, we have r equals 2 secant theta. And kind of like solving a trig equation, we want to rearrange this so that we end up with one of those relationships that we like to play with. The x squared plus y squared equals r squared, or x equals r cosine theta, y equals r sine theta. So I remember that 2 times secant is the same thing as 2 over cosine theta. So multiply both sides by cosine theta. R cosine theta is equal to 2. Let me put a little arrow between there. X equals 2. It's just a vertical line. There's the pretty picture. Rewrite this polar equation as a Cartesian equation. So let's see if this one's as easy as that one was. Example 8, we have r equals 3 over 1 minus 2 cosine theta. Well, first thing that jumps out at me is to multiply both sides by this denominator here. So r minus 2 r cosine theta equals 3. So you can see I kind of cheated there. I multiplied and distributed all in one step because r times 1 minus 2 cosine theta, I went ahead and distributed. So r is equal to 2, r minus 2x, not equal to, r minus 2x is equal to 3. So now what I want to do is get my r by itself on one side of the equal mark. So I'm going to add 2x to each side. R equals 2x plus 3. Now I'm going to square both sides. So r squared is x squared plus y squared has to be equal to 2x plus 3 squared. Yeah, they're not pretty Cartesian equations. They are complicated implicit equations. And let's look at the answer. Oops. There we go. We end up with x squared plus y squared equals 3 minus 2x. Did I make a sign error over here? Let's see, minus. This was minus. So yeah, that was plus. It looks like I made the sign error over here because this was minus r minus equals 3. So r squared equals yes, I made it over here. Okay, I'm going to fix the PowerPoints, don't worry. We got them right on my written notes. And now we'll go back and practice. So give these a try and then we'll meet back and we'll compare. Okay, A required kind of a little trick that we hadn't done before. We wanted r squared over here, but squaring both sides wouldn't help us. So we multiply both sides by r. And that way we get an r over here on the right-hand side as well, and we end up with 2r sine theta, which is just y. So x squared plus y squared is 2y. B was too easy. It was exactly like the example. We just rewrote secant as 1 over cosine. C, we had r equals 4. Well, I squared both sides and got r squared is 16, so x squared plus y squared equals 16. So when you have a trig function, try multiplying both sides by r. If you don't have a trig function, just square both sides. This one, not too bad. I multiplied both sides by my denominator here. I ended up with r times cosine theta minus 5 sine theta equals 1. I distributed, and then I replaced r and r cosine theta and r sine theta. The next one was quite tricky. First, you had to use the double angle identity because you can't do anything with r's and 2 thetas. It's got to be r's and thetas. Then I had to take these relationships that I've been using and rearrange them. Cosine is x over r and sine is y over r. So I replaced sine with y over r, cosine with x over r, and I also used the fact that since r squared equals x squared plus y squared, then r, well, it's really plus or minus, but x squared plus y squared. So we used that relationship and this relationship. So we did a lot of rearranging of our relationships. You got lots of lab manual practice and lots of WebAssigns. Get busy. You can do this.